Good evening, everybody. Tonight we're going to be doing a video on the well-known Mobius function. And mu of n, it turns out it has what they call a tri-valent definition, I guess. But I think this is called the Mobius. I think it's a German word with the umlaut, the double dots above the O. But it's Mobius. I'm not sure if I'm pronouncing it correctly. And it's a function. And I'll just abbreviate that. Okay. Now it has a strange looking definition. I learned a little bit about it, abbreviated function right there. I learned a little bit about it when they were in Charles Vanden Eyndens number theory book, when he was talking about inverses of arithmetic functions. An arithmetic function is just a function that maps the integers to the integers, basically, or maybe the natural numbers to the natural numbers. And the finding an inverse is of interest, and this Mobius function pops up a little bit. Okay, but anyway, we're supposed to show that mu of n, that's called mu, mu of n times mu of n plus 1 times mu of n plus 2 times mu of n plus 3 is equal to 0 for all n. And y'all, n here, of course, is just the positive integers. I'll just put this, it's the set 1 to positive. Sometimes people want to include 0 just for convenience, but it's not important here. So ad infinitum, okay? So it's just the counting numbers, all right? Now, so we have to provide a definition here. And this is a strange looking definition if you haven't seen the purpose of it. It seems like it's almost arbitrary or something. But by convention, mu of 1 is 1. And then mu of any natural number that is divisible by a prime squared is always equal to 0. Now down here, this third part, I left out. These primes here are distinct. Let me put that off to the side here. Each of these primes are distinct. And just a nice little sanity check on this thing is to notice that this is a definition for all natural numbers. Now you may think, well, it doesn't look like it. But you see, if these are all distinct, that means it's not divisible by a perfect square, because a perfect square would have to contain a square prime as a factor, right? So these are all distinct. So this is a definition over all natural numbers. We defined it at 1 to be 1. We defined it to be 0 if a square prime divides the input, all right? And then if these are all distinct, there's no way the square prime could happen there, right? So this covers every single prime number. Its domain is all natural numbers, all positive integers, okay? Now let's take a look at a concrete example here and just make some sense out of this definition. So mu at 5 would just be equal to minus 1 raised to the 1 power, right? Because it's the only prime. So you see the t would, let me just off to the side here, for t would just be equal to 1, right? Trivially, it's kind of almost not empty, but so it would be, so this part's minus 1. Now notice that 6 is 2 times 3, all right? And so you would have minus 1 quantity squared. And again, folks, that's because 6 is 2 times 3, so there's 2 primes, and that means t would be equal to 2, so you would square this. So this becomes 1. And in a similar fashion, this would be negative 1. This would be negative 1 right here. For the same reason, this was negative 1. All right. Now, right here, notice this guy right here is going to be equal to 0. And why? That's because 4 squared, or 2 squared, divides 8. 2 squared is a divisor of 8. 2 squared is equal to 4, and 4 certainly divides 8, right? And you see, that's this part of the definition right here. Okay? So this object right here would be equal to 0, and all these others, it doesn't make any difference. The whole thing is equal to 0, right? Now notice this is 4 consecutive integers in the form that the original problem specified. All right, so it happened for this one, but this certainly does not constitute a proof for all n. Now let me write down a lemma here that's fairly clear. I mean, it makes quite a bit of sense. Exactly 1 of 4 consecutive natural numbers is a multiple of 4. And you can think of any of them you want, like if you did 11, 12, 13, 14. Well, 12 would be a multiple of 4, right? If you did 19, 20, 21, 22, 20 would be a multiple of 4. So in any consecutive group of positive, four consecutive positive integers, exactly 1 will be a multiple of 4, okay? And if you're a multiple of 4, that means that you're divisible by 2 squared, right? So that's why this works. So just to be, and again, I'm not going to try to do a full, the proof of this is fairly mechanical, and you got to cover some cases, but notice this case right here would be the case 4k plus 1. Okay, that would, for 5, this would be 4k plus 2. That would be, k of course is 1 in this case. 7 would be 4k plus 3. And you see you're guaranteed to run into a multiple. And then 8 finally is 4k plus 4. Let me write this, 4k plus 4. We got room, yep. 4k plus 4, right? So you see, again, this was in the form 4k plus 1 for 5, 4k plus 2. So this part right here would be divisible by 4. It doesn't make a difference if you started with 4k plus 2, you would eventually run into 4k plus 4. If you start out with 4k, you would be done, right? So there's exactly one multiple of 4 in 4 consecutive integers, okay? Exactly one of them is a multiple of 4. But notice that 2 squared divides any multiple of 4. And let me just write that as 4m. And that's manifestly true, right? 2 squared, and you see this is the p squared that we're talking about, right? This is the p squared that we're talking about in this definition that gives us the 0, right? So anyway, that really more or less completes the proof. In other words, one of these has to be divisible by 4. One of them, the first one, the second one, the third one, or the fourth one. And it doesn't make any difference that the others are equal to 1 or negative 1. All you need is 1, 0 as a factor here, and you're done. Okay, so perhaps I should say just a bit more. N plus 1, if you have n plus n plus 1, n plus 2, n plus 3, and I don't know how to make this, but one of these is a multiple of 4 by the reasoning that we used right here. Okay, so that completes the proof, folks. I'll go ahead and say QED. In other words, one of them is going to be, and maybe a nice way to say this would be 2 squared. Yeah, this kind of caps it off. This is the way to do it. 2 squared, which is p squared, okay, is going to divide n plus I. I'll call this an I. Okay, and let me write that parenthetically. Okay, so 2 squared divides n plus I, where I is equal to, for one of for some I in this range. Okay, not all of them, but for some I, for one of the I's. Let me just write one of the I's. There's probably a more formal way with the notation to do this, but just one of the, let me write this, one of the I's, like this. Okay, is that, okay, but for one of the I's, the 2 squared is going to divide it, and if that happens, one of them is going to be 0. So in other words, you would have mu at that is equal to 0, right? For one of the I's in 4 consecutive. 1, 2, 3, 4. All right, y'all, I'm sorry, I could have just said done almost right here, but I just hope it made sense, and thank you for viewing.